So this automation lunch and learn, I wanted to go over what we're adding into metrology.net related to calibration, drift, and control charts. So as we're doing more and more of the higher end automation, we're having to keep track of things like cal factors and drifts and things like that. So we wanted to get it integrated into the platform. So I'm trying to make all of these about learning. So every one of these is going to start off with what the learning objectives are. So every one of the lunch and learns is going to cover some object-oriented programming and things that we do in the VB.net. So, and I'm a big proponent of object-oriented programming because when you get good at object-oriented programming, a lot of things become a lot easier. You think about how you code and organize your code. So I'm hoping that'll be a walk away. Somebody will get another representation of bringing something into an object-oriented programming state and seeing what the advantages of when you think about it as objects. So this one, we're going to cover the work we're doing in control charts and calibration drift. We want to cover some basic things you might need for ISO 17025 uncertainties, though that won't be the core of this, but I will cover at the end how you can integrate this into your uncertainty budgets. So, and then we'll cover a little bit of customizable uncertainties without changing code. And that's one of the things that's that I see change a lot is our uncertainty budgets will make a lot of changes. But if we have, if we put all of our uncertainties inside of our code, then every time our uncertainties change, we've got to go in and adjust our code. So we want to be able to separate those things out, or at least wise have a good model for how we do our uncertainties external from our actual code, so we don't have to do as much support and maintenance over time. So little bit about CalLab Solutions. I think everybody out there knows this. So, but we do a lot of software building and consulting around the metrology world. And we're really more of a metrology consulting company than we are a software company because we help companies come in and get their automation up and running. So I like to bring this slide up because it'll get a lot of people, some people it gets underneath their skin, but the better, cheaper, faster. We have to do that with our automation, you know, and to be productive as a calibration lab, we have to do things better, cheaper, and faster because whether we're a third-party lab or an in-house lab, if we don't continually look at getting these efficiencies and be better at what we're doing, then we're either going to get outsourced or somebody's going to come in and actually replace us as a calibration provider. So we've always got to be thinking about this. How can we do things better, cheaper, and faster? And I like to iterate upon that doesn't mean that we're trying to do things and be less accurate. So we can always work at being more accurate as part of that better thing as to what we're working on. In the software world, one of the things that really drives me crazy is people start tackling a software problem before they have a good definition of the problem. So I encourage people that when you're working on a software project, you're always coming back in and you're looking at what is the problem in the problem domain. So the problem that we had is we have these high accuracy, you know, DC resistors and 10-volt cells, and we know they're going to drift over time, but as we're trying to get that best accuracy out of them, we need to project what we think or predict what we think the changes are going to be over time. And we need to do this in such a way that we can also pass that information on to an auditor so that the auditor can see what's going on with our calibrations and say, okay, we're buying into your uncertainty estimates or we're not. So right now, a lot of calibration labs will do that work, and they'll do that work inside of Excel. And Excel is a great solution for a lot of the mathematical problems we have. But we have a problem of the cost that we're going to have in maintaining Excel sheets. So every time an auditor comes in, you know, you'll see the calibration labs out there. They're going through and updating all their uncertainty budgets, getting it ready for that auditor coming in. So there's a cost of getting all your Excel put together as opposed to making this something you're doing just as a daily basis. And what we wanted to do in the problem statement is we wanted to get that built into our automation software. So our automation software is just doing this inherently and natively. And the next version, or the next one of these, is going to be on getting the computers to actually start collecting that data that we're going to use for our drifting and trending, so that we can do this work every single day or week or however often we want to come in and get more data. Quick review out there. I want to put a big thanks out to Jeff Gust for the training he's done at the NCSLs on drift analysis. And then Rob Thomas, he was the one who was teaching me how this drift is running and helped me go through some of the code that I was working on and gave me some mathematical proofs. Anytime I try to automate something, I like to get a mathematical proof of it so that I've got an external data, and then my code can generate the results exactly the same that's done with these mathematical proofs. So validating and verifying that the code and the mathematics in the code is running correctly is part of what we want to do in our process. What we got in as an example was a 1 ohm Fluke 742, and it had 6 calibrations over a 5-year period. And each of those calibrations had an uncertainty or had a measured value and an uncertainty value. And we were able to grab that data, or that data came to us all packaged up and put into a spreadsheet. I'm not an expert on drift analysis or trend analysis or regression. So these are all examples that were given to me that we dug through. So I'll switch over here real quick to the spreadsheet put together by Jeff Gust as part of his classes that were put out. And you can see in here, we've got our calibration data. And inside of here, we've got our 6 calibrations and our measurement uncertainties and the dates that we brought out of this. And what we want to do is grab this data, and we want to be able to predict the value and the uncertainties. So part of what was done in the spreadsheet is they did the predicted values at the same dates based on numbers that were put in here, doing the best fit straight line drift trends analysis. So they were able to take all of this data, best fit straight line it, and get out their predicted values that come with this. And then with that, taking the uncertainty numbers, they were able to do the upper and lower bounds. And the idea behind this is they want to take this data and predict how things are in the future. So as 1/6, this would be the value they would get back, but you can come in and change this to 2/6, and you'll get back an uncertainty value or a new ohmic value and the uncertainty of that value each time you put in a new date. And that was the idea behind this predictions. So when you start looking at the graphs, you have the control chart. So zoom in here so everybody can see this. So on the control chart, you're going to see here that you got each one of your values over that period of time plotted. And as it's plotted, they're putting the upper and lower limits on there. And from the fit trend line, you can see that they also fit an upper limit and a lower limit inside of those trend lines. So those are going to be your upper bounds as what we're projecting. And you can see it'll allow to have a measurement or two that might be falling out of the window, but the trend line will always keep that trend line running. So this comes back into the prediction graph. So inside of this prediction graph, you can see that you can push this prediction graph on into the future for a period of time that you're feeling confident with. You can keep your trend running. So also in this spreadsheet, and I can share this out if somebody wants to run through this, but also in the spreadsheet, they've got the math behind doing the the regression of the uncertainties. And you can see in here that they're grabbing in all the values and calculating out the dates. And this is what's going to be important, because when we graph these out, we're graphing them out by the date we grabbed it, but we're going to do all of our mathematics by a time period. So we need to know the delta between each one of these times. And this was one of the things key in the calculations, was coming in and doing all the math to get all of these pieces of data out. And all of that gets pushed into these values that run into the graphs, and they come back into the cal data to give you your predicted values and your upper and lower bounds along with your uncertainties.
Hey, Mike, could I just ask a quick clarifying question? I see the word upper bound. Are we calling that something more specific, like pass-fail tolerance? Bound just isn't a common metrology term.
Yeah. I don't believe it's pass-fail. I believe the upper and lower bounds is just so they can look at them, so they can get things are supposed to be falling, and it'll.
This is Brian. This is the control limit. It's called control limit. It's a trend chart.
Yes. So then control limits define that. Are they using this to determine the pass-fail of the resistor as found for the calibration? Because I'm also seeing the uncertainty bars around the chart that you have up right now for the measured value.
Yeah, that's
incorrect. Uncertainty of the projected value. Is that what we're seeing as the upper and lower bound?
It's from the standard deviation. Should be from the standard deviation, and 2 sigma or 3 sigma. It's up. Right. Depends on
Of what? The predicted value?
No, the bound is based on the 6 data you have, right? So you calculate the standard deviation, and you can step the 2 sigma of the value or 3 sigma of the values as your control limits. So when if you set it to control limits over, right, then you have to investigate what's going on.
What value though?
Oh, well, you can set a 2 sigma, 3 sigma is up to you. Depends on your confidence.
Yes, I understand we're looking at a k equals 2 value of what?
Standard deviation.
No, not of standard deviation. That is the standard deviation. It's of what? It's a deviation around something, and it looks like it's the predicted value, but I can't exactly tell.
Yeah, but because you have 6 data, right?
I don't think I'm quite coming through clearly. Again, I'm just asking clarification. I think it's of the predicted value or the regression value, some at that point in the future.
Yes.
That's the uncertainty of that value. The k
it's
equals
not,
2.
It's not called uncertainty. Yeah.
Yeah.
Uncertainty is the bar. The bar you see over there. That's the bar. The reading plus minus. That's the uncertainty. The control limit is established based on the 2 sigma of the 1, 2, 3, 4, 5, 6. So the 6 data points you have. Yeah.
I come from SPC background, so when we start calling control limits, that's a pass-fail tolerance, and I don't think that's what we're dealing with here.
You don't call it pass and fail. No, the 2 sigma is.
It can exceed that upper or lower control limit. That's my pass or fail in a normal SPC world where I'm calling this upper and lower bounds. I don't think that's what it is. I think we're actually looking at the k equals 2 uncertainty of that regression number out in the future, right?
What do you mean by uncertainty? Uncertainty is from the measurement data. Is not from the uncertainty is the major data.
Never mind. Mike, back to you.
Yeah, I'm not a mathematical expert on this, so I can only make some assumptions in what you're seeing in here. And I think, Travis, you're kind of on it, that this right here outside of our control limits is saying, hey, we need to go back in and take a look at that. That may have been a bad measurement, or we may.
Yeah, you were one step ahead of me in the chess game. I was going there, but again, I don't want to distract from the main thrust of your presentation, though, Mike.
Yeah. So. But the idea is going to be that we can use these and get our predicted values out of this, and we can go back in and run it. So to me, this control chart that you're looking at here is something you're going to get out of it. Look at your upper and lower bounds, and you're going to be able to look at these upper and lower bounds and make decisions. Are my assumptions working correctly, or do I need to go in and adjust my upper and lower bounds and increase my uncertainties or my uncertainty prediction so I can stay within my control limits? So the big thing that I wanted to show here is when we come into this Cal data, and I wanted to show how these spreadsheets are great tools, but when we start looking at these spreadsheets, we've got a lot of maintenance that we have to do on these. So you can see that if I wanted to come here to this field and I wanted to come to field 40, B, and I wanted to grab my value out and I wanted to come into 46A and grab my uncertainty out, you can see that I have a problem that the next time I put a piece of data inside of here, that I'm going to shift all of those rows down. So I can't rely on using this spreadsheet without having to come back in every time I'm going to use, or every time I'm going to calibrate this, I've got to come back in and I've got to re-engineer my spreadsheet. So I've got to put more data in here. And then I've got to come into my regression data and I've got to put more data points in here. And that causes all of my things to shift down. Excel does a good job of keeping track of these things, but you can see inside of here, I'm going to have to go in and I'm going to have to edit that field if I go in and add another field. I can't just add in a row and this field is going to automatically update for me. So every time I go in and make a change to my spreadsheet, if I didn't design it easily or correctly, I've got to come in and update all of my fields and make sure every one of my fields that are running calculated values comes in correct. So that creates a little bit of maintenance for us if we're going to go to something like Excel. And that kind of gives us some problems with that better, cheaper, and faster things that we're trying to do. So, and I'll give this code out to anybody that's looking at it, but this is the object-oriented code that I put together that I'm using for the core of this. So we know that for me to run this is I've got to have myself a cal value, and I've got to have an uncertainty, and I've got to have a date. For ease of use, I go ahead and I calculate the days that I'm going to use in my graph because I need those delta days. And you can see from this function that I'm using, which is going to be a shared function. So that means that the function runs without the object being instantiated. And it's going to give me back a new cal point. So I give it the date, the value, the uncertainty. And it's going to create a reference date of 1900, and it's going to use that reference date of 1900 to give me all my delta days. And playing with the math, it doesn't matter what my reference day is, as long as I always have a valid reference day that I pull things from. So then as I instantiate it, I put my days in, put all my values, and I return back to the object that new representation in code. So inside of the Excel file, if you can imagine, I can just magically add more data, more data, more data, more data, and that Excel file's calculations would always update itself. So these were the things I had to pull in with my core data. So now in my control chart, I'm going to maintain a list of cal points. So that section of code inside, or that section of cells where I'm adding in my data points, this is what's going to allow me to add more data, more data, more data to my object. And then my object is going to go through and do the work for me. So the first thing I need it to do is calculate out my slope. So, and I'm not going to do a review through this. I've checked all the math on this. But you can see we can come in, and this function out here is going to average these things, and these functions are actually going to sort my items by the days. So by the number of days, it's going to reorganize my data. So now I can put my data in any order that I want to put my data in for it to go in and do things. And I can remove a piece of data if I need to. And these inline functions here, these guys are just going to sort my data out to where I can get the average of my days sorted the average of my cow values sorted. So I can go in and grab these, and this is going to calculate out my slope. And then this function here is going to calculate my intercept based on any set of data points that's put into my list. So that would be an example of how we come in and we use that object-oriented programming to where we can come in and use these tools that are allowing us to do things quicker. So jumping down to the next slide here, we want to get out our predicted value. So we're getting out our predicted value by taking the number of days times our slope times our plus our intercept. That's going to kick us out our predicted value. So now we can take that slope and get any point there that we want to get, or any point in the future, or inside of the best fit straight line. We can get out our nominal value. And I had to use vdate or ddate because date is a keyword. So you'll see that in here that .NET or the VB compilers will try to use the date because it's a type. So we had to come in and call it a vdate or a ddate or something like that. So now the regression, this is the tough part of this, was going in here and getting this regression running. And I'm not going to do a proof on the math here. But the reason that I named all of these variables, and I could have put this in one big function, but the reason I name all of these is so that I can come in and do my audit. So when we look at this spreadsheet out here, we can see that here are the key values that they want, okay? But inside of here, I can come in and get the number of cows, I can get the sum of the squares, I can get the sum of the calibration time squared. So when you look inside of my code that I have, you can see that I've got my sum of my squares value. I got my sum of my days. I've got the sum of my square days. So I write my code out long-handed like that so that I can come in and audit the code, stepping through the code with each one of my values. And that just makes it easier to create that audit trail. So when somebody's going to audit your code or somebody's going to come in and want to review it or want to see a proof of it, that they can dig in and look at it line by line. So then what we also want to do inside of a code review is you'll see inside of here, I've got the exact values that came out of the spreadsheet. And I want to be able to load those items inside of the spreadsheet. And I want to be able to come in here and grab these values out and see that my code can generate the exact same code as the spreadsheet. And one of the things you're able to do inside of .NET is there's things out there that you can add on that will be unit testing. And you can use unit tests to actually go out and test your code. And you can even tie the unit tests inside of your QA program to where no programmer can check code in until it's passed the unit test. So that gives us a lot of power to make sure we're keeping the quality up. So now what I'm going to do is jump over to the code and we'll run through the program. Knock on wood that it'll actually run, because some days programs just don't behave like you want them to. So, all right, you can see in here that I've actually got my code. I'll stop this and maximize it. I'll stop it and I'll zoom in just a bit so people can see it a little bit better. All right, so I can start this up and you see it'll start up and it'll hit my breakpoint. It will start up and it'll hit my breakpoint. And now you can see that I'm going to add into my chart. So I'm going to add in line 1, line 2, line 3, line 4, line 5, line 6. So I got 6 of my cows. I click this, it's going to give me back my slope. And I can see, I can jump back to the spreadsheet. And I can see the slope on my spreadsheet is going to match up. If I can remember where the slope was. Okay, here we go. So here's the y-intercept. Where is my slope? That's my slope. So 5.72 e to the minus ninth. And if we come back into this, we can see that I can grab my slope down, and I can actually multiply my slope by 1e9, and it'll bring that over. So 5.729. So then we can look over at the intercept, and we can see the same thing happens with the intercept. Is I've got my intercept value to 9998. Jump back to our spreadsheet. We'll see that we've got correlation between those numbers. And continuing through the code, I can get my predicted value at a date, and I can get my predicted uncertainty at a date. So I can see each one of these values is going to reach in. I can drop this down and multiply it by 1e6, and you'll see that we're 0.549 is where we're going to be for our predicted uncertainties. And we can jump back into our spreadsheet, and we can see that we're able to correlate those numbers. So that's what we did to come in and prove this. So now with this code, if I want to add another line of code, I can just reach in here and add another cal date. All I have to do is reach in here and push the values into it. I don't have them running, but my chart has a save file function, and it has a load file function. Okay, so I can actually now have all of my data, reach out, chart it out, bring it back. I also have, and this is one of the things I like about .NET, I can actually reach into my chart, and I can say, while my code is running, I can actually export my data out to a place. So now if I reach down to this line of code and I execute it, I can go over to that directory now, and I can see that it actually created something that I can reach out and hand to my auditor to show him the math behind the code if he doesn't want to dig into the underlying code. Open it up here with just Notepad++. But you can see in that spreadsheet that we use for our validation, you can see that I've got my date, my measured value, my measured uncertainty, my predicted value, my predicted uncertainty, my upper bound, my lower bound, and each one of these columns are in here separated out by tabs. So I can import it, I can cut and paste it or load it into an Excel file and not have any kind of problems. So, and I don't know, since Brian's out there, Brian, do you think this would suffice as an audit if I showed all the code behind it? Because I know you actually go out and do audits.
Yeah, I don't see any issue with that. Yeah, that's supposed to demonstrate that. Yeah.
So that's kind of what I wanted to do, was have the code to where it's easily auditable out there for people. All right, jump back here. So learning objectives, these were the things I wanted to hit across, was the object-oriented programming. I will make a copy of my class out here and put it out as part of the code so people can come into it, and hopefully some people come in, even audit it, just in case I made a mistake out there, which knock on wood, hopefully I didn't. So, but they can come in and audit the code and audit what we have inside of the class that we built. Then jumping back down, covered part of what we're doing with control charts and drifts. The ISO 17025 uncertainties, there's going to be more that you have to include in this. but you can take and you can see how the data files that you're using in code, that they can be passed off to the auditors, and you've got that separation between the code that you're running and your data files and how you can report something out to the so now inside of your code, when you want to get the uncertainty for a value and a calculated value, you can reach into this line of code and you can grab for whatever date you're running the calibration. The difference here is this date would actually be in now, is the word you use in .NET to say, get me the date and time as it is now. But when you're running your code, you can reach in and grab those values out of your data format with the object. So that's what we wanted to do, was be able to customize the values that we're using without actually having to go in and program that into our code each time. So questions, comments?
This is Jack. Question, will we be able to get a copy of the spreadsheet? It'd be interesting to look at that more closely.
Yeah, I'll put a copy of the spreadsheet out there and a copy of the code. So, and then with the presentation, anybody who's got, a copy of Visual Studio can come in, grab the class, and run through the code and test it.
Thanks.
Those people who are new to this, is you probably won't put it out like this where it's a tools control chart. So I wrap that up with a thing called Namespace. So Namespace allows me to keep a lot of functions in different places. It kind of allows me to organize my functions. So underneath tools is in metrology.net. So it's metrology.net.tools.control chart. So I'm putting all of the mathematical tools I have underneath the tools function.
I have a comment about the spreadsheet. I think, this is Brian. Even I think the idea is to figure out the drift, but I'm not sure, that's the approach, you analyze the drift. The things you are doing right now is SPC. If you look at the Excel, right, what he's doing is using the 2 sigma as a control limit. I saw it over there. But there's another way you can, just to check whether the system is drift out of the spec, because some product has a drift spec. So you can use it as your limit, as your spec, or as your control limit as well. So it depends on who that so-called bounds over there, what is established for. The question is, how do you analyze drift? So it was one artifact, one device, you just cannot figure it out, because there are 2 variables over here. One is the system, one is the device under test. Both are changing. So is that number?
The device under test, but this is set where you've got your resistor, and you're sending your resistor out for calibration, and you're bringing it back. Is typically what calibration labs will do for their drift.
Yes. So what I'm saying, that's what I'm saying, is the drift of the device, or is the drift from the measurement system by the vendor?
Oh, yeah. That would be something outside of the scope of what I'm trying to do with this to figure out.
Understand, yeah. I understand, yeah. I'm just saying,
that would be covered in the calibration uncertainty that the vendor gives you.
Yeah. Well, we don't know yet. Yeah, that's what I'm saying. That's something you have to investigate, yeah.
If they don't include that, you need to find a different vendor.
Yeah, that's what I'm saying. It's what I know. The way Jeff called this, I think he presented just last week as well. And it's similar. I'm just asking, the definition of drift, and you have to, actually find out. It's not just taking those data and do the linear regression.
Yeah, I'm sure this data is sample data. It's probably not an actual device that's being used, because I haven't had the opportunity to sit through one of Jeff's classes yet, so it's on my to-do. I'm more of an RF and microwave cal guy, so as I'm dropping into this DC and low stuff, I'm learning a lot of things about how DC and low and how that calibration world will do a lot of things. And at first, every time somebody would talk in parts per million it would just blow my mind how quickly they could come in and tell you, well, I'm only off by 3 parts. You know, that's just common language. Well, in the RF and microwave world, we don't talk parts per million. We talk dBm. So so it's like learning a whole new language when I'm talking to a lot of these guys.
I agree. RF microwave people are really non-linear.
Yeah.
He is a DC and LF person.
So any more questions? Okay, I'd like to thank you all for attending this week's Lunch and Learn, and hopefully there'll be more of these in the future. Thanks.